The San Andreas Fault system is a transform fault that connects the seafloor spreading in the Gulf of California in the south to the Mendocino Triple Junction in the north. The fault passes through highly populated areas of California and has generated numerous destructive earthquakes in history. Between major earthquakes, the relative motion between the Pacific Plate and the North American Plate causes elastic loading of the crust that can be observed as deformation of the surface. This deformation is being measured with a variety of tools, including about 700 continuously operated GNSS sites, as well as repeat pass radar interferometry. The combination of these two methods provides both high accuracy over large distances and high spatial resolution. Introduction. Here we take you on a tour of interesting signals that appear in the INSA deformation maps. These are overlays to Google Earth showing the line of sight velocity derived from Sentinel-1 satellites between 2015 and June 2019. These swaths were acquired on descending orbits, northeast to southwest, where the satellite is looking toward the northwest and down. The red color indicates ground motion toward the satellite, and the blue color indicates ground motion away from the satellite. A second color is added to the semi-vertical maps to illustrate rapid signals, mainly associated with subsidence in the Central Valley. The tour begins with strike-slip faults and stepovers, then continues with vertical signals associated with extraction and recharge of groundwater, petroleum, and geothermal fluids. Finally, we visit some curious dry lake beds that appear to be uplifting and never subsiding. 1. Active faults and stepovers. The most prominent deformation feature is the large-scale, right lateral, strike-slip motion between the North American Plate and the Pacific Plate, which is about 45 mm per year. The transition is broad where faults are deeply locked, and very sharp where faults are creeping, with maximum creep rates up to 30 mm per year at the creeping section of the San Andreas Fault. To the north, the Hayward Fault also experiences surface creep, between 3.7 to 6.5 mm per year, consistent with previous studies. Moving toward the south, at the Parkfield Stepover, there is a zone of subsidence, probably related to groundwater extraction rather than tectonic subsidence. Turning on the transparency, one can see farms in the sedimented basin of the Stepover region. Further south at the Mojave section of the San Andreas Fault, there is a broad transition related to interseismic deformation along a more deeply locked fault. Moving into Southern California, there is a stepover along the San Jacinto Fault that has a history of subsidence due to groundwater extraction. Currently it is subsiding at a rate of more than 10 mm per year. A similar stepover of the Elsinore Fault has uplift due to groundwater recharge associated with the Temecula Valley Basin Salt and Nutrient Management Plan. At the Coachella section of the San Andreas Fault, surface creep has been well documented for the past 300 years. The average rate is 2 mm per year, though on decadal timescales this rate is observed to vary considerably. The most recent significant creep event along this section was triggered by the 2017 Chiapas earthquake in Mexico. Just to the south of the Salton Sea, the Superstition Hills Fault is known for its spontaneous creep events. The observed average creep rate is 7 to 8 mm per year. This is mainly due to one event in 2017 with over 30 mm of creep. 2. Extraction and recharge of groundwater. Some of the most prominent signals in the velocity maps are associated with groundwater extraction and injection. These become more apparent in the line of sight velocity by removing the horizontal tectonic motions to create a semi-vertical velocity map. The removal is not perfect, due to a lack of resolution in the GNSS horizontal velocity model. So for example, there is an artifact along the creeping section of the San Andreas Fault. The signals in most other areas, blue is down and red is up, are related to hydrological deformation. Just north of the creeping section is the Santa Clara Valley, where the local water district conducts a recharge program. The ground shows uplift over the period of the satellite observations. Note the Quaternary Silver Creek Fault acts as a natural barrier and splits the uplift signal. Moving to the southeast, into the Central Valley, the San Joaquin Basin is subsiding rapidly. Using the transparency, it is evident that this subsidence is related to rapid water extraction, especially during the California drought. Moving further south, near Tula, the ground subsidence is more rapid, with the largest rate over 400 mm per year. Just next to the northwest, there is a region of overall uplift aligned with the San Luis Canal. The inset time series plot shows rapid subsidence between 2015 and 2017, followed by a period of rapid uplift. Outside of the Central Valley there are smaller areas of prominent subsidence and uplift. For example, the Kuama Basin shows some subsidence perhaps associated with water extraction. A similar subsidence signal is seen in the Lancaster Basin. Further to the south, the Los Angeles Basin has a long history of seasonal subsidence and uplift, due to underground water storage, especially over the Santa Ana Basin. The time series clearly shows the annual cycle as well as the current overall upward trend. Moving east, to the north of Palm Springs, there is significant uplift due to groundwater recharge, with most of its signal coming from year 2017, when the uplift was over 60 mm. In contrast, the golf courses in the Indio region are subsiding, but at a much lower rate than before 2010. Finally, we note a zone of subsidence in the Chula Vista Basin just south of San Diego, that is perhaps due to depletion of groundwater. (3) Extraction and recharge of oil fields. Oil fields are also prominent sites of vertical deformation, associated with petroleum extraction and water recharge. In California, there are more than 60,000 active wells that produce over 150 million barrels of oil each year. We observe a number of subsiding oil fields around Bakersfield, such as prominent deformation at the Elk Hills Petroleum Reserve. The production area is evident by turning on the transparency and zooming in to reveal thousands of pump jacks. A plot of the semi-vertical time series shows steady subsidence of more than 120 mm during this 4.5 years period. Moving to the northwest, there is similar subsidence at the Lost Hills and Belridge oil fields. Over the observation period, they are subsiding at a rate around 50 mm per year, which is almost 10 times smaller than the rate observed by the EARS satellite 20 years ago. Moving to the east, the oil field near Kern County has a similar subsidence rate, but primarily on the west side of the Kern Front Fault. It's interesting to consider the loading or unloading effect from the oil production on this normal fault. Four, extraction and recharge of geothermal fluids. California is also rich in geothermal resources. Production of geothermal energy usually involves extracting and re-injecting fluids, which causes both subsidence and uplift in the vicinity of the reservoir. We begin the tour in Northern California at the Geysers geothermal field. Geysers has over 350 wells and a capacity of 1,200 megawatts, making it the most productive in the world. Despite this large production, the surface is not subsiding at a high rate, mainly because of the Santa Rosa Geysers recharge project. This recharge not only reduces the hazard due to rapid subsidence gradients, but it also increases the amount of power that can be generated. Moving south, the Coso geothermal field on the edge of the deformation map shows a subsidence rate of about 20 mm per year. We are expanding the analysis area to better resolve this geothermal field as well as the large deformation associated with the 2019 Ridgecrest earthquakes. Moving into Southern California, there is significant subsidence at the southern end of the Salton Sea. Due to a combination of geothermal production and groundwater extraction, much of this area is decorrelated due to extensive farming activities. One would need to perform persistent scatter analysis to retrieve reliable signals along the more stable roads among the crops. Moving further south, there are two more geothermal fields near the US-Mexico border, Heber and Ormesa, that show areas of subsidence and uplift. South of the US-Mexico border is the Cerro Prieto geothermal field, which is the world's second largest in terms of energy generation. This field is at the step over between the Imperial Fault and Cerro Prieto Fault, and the subsidence is highest on the eastern side but terminates at the southern end of the Imperial Fault. The peak subsidence rate in the region is more than 160 mm per year. Considering the already low elevation, the area will be below sea level in roughly 65 years if the current subsidence rate continues. 5. Dry lake beds. One of the more perplexing signals seen in the semi-vertical velocity maps are dry lake beds that appear to be uplifting during this period. The largest is the Laguna Salada in Mexico. In Central California, Soda Lake is uplifting. And in southeastern California there are at least 5 lake beds that are uplifting, including one at Xixx and 4 near Amboy. An examination of the line of sight time series at these lake beds show they are always uplifting at rates ranging from 15 to 20 mm per year. This is a puzzling observation and we are not sure whether this continuous uplift is real signal or an artifact of the INSA processing in these areas of localized lower coherence.